Okay, start again. Last time we were together, we looked at displacement versus time. Now we're going to look at velocity versus time graphs. These are much more complicated than good old displacement, which is really only needs a mathematical level of about year 8. Okay? This one, however, we need to have a look at because we are changing velocity. And as we know, changing velocity has a definition. What is the change of velocity? Any change, it is automatically acceleration. So whenever we see a change in velocity, we are looking at acceleration. So let's have a look at what we've got here. So this is the first of the graphs that you are going to be working. And like we had last time, you're going to be cutting these out and you're going to be annotating them around. So I'll give you a few moments to cut out this graph that you see here and stick it into the centre of your workbook on the page so we can annotate around it. Okay? Okay, let's have a look at this graph here. Firstly, the two axes. The horizontal, once again, remains as time. Time can be measured in any unit, but it's best if it is in seconds because that means we can have it per second and so on. And the vertical axis is velocity. If we are, there's the origin over here. So here's the origin of the graph. That's the origin of the graph. It's not the origin of the motion. It's the origin of the graph. That means that if there is an axis above the origin, this is motion forward. So all of this graph is describing motion forward motion. This object, even though parts of the graph tilt backward, say this part here, that is tilting backward, that is still motion forward. All of this graph is motion forward, away from a specific place. Okay? It only becomes motion backward if it is underneath the axis. So let's have a look at what all these things are determining. At time equaling 0, we are at zero velocity. So what is zero velocity? What's another way of saying zero velocity? You're not moving. So it's a 4-letter word. Stop. Good. We are stop. So this is stop. Okay. At time equaling 3 seconds, up here, what am I? How fast am I going? Just looking at that. At time equaling 3 seconds, here is 3 seconds. How fast am I going? Looking at here. I'll ask the question again. Very, very carefully, just looking up here rather than anywhere else. At time equaling 3 seconds, how fast am I going? It's not a trick question. I'm travelling at 3 metres per second. So at time equaling 3 seconds, I just read off how fast I'm going. This is a travel graph. At time equaling 2 seconds, how fast am I going? At time equaling 5 seconds, how fast am I going? 6 metres per second. Okay? So it's just simply reading sideways. So I can ask you at any time, at time equaling 7 seconds, you are now travelling 5. So this graph is showing you that you are changing your velocity. That means that you must be getting faster or getting slower. You must be accelerating. So if I'm accelerating, so here's time equaling 3, I'm now travelling at 3 metres per second. No, sorry, I'll just reverse that. 3 metres per second. Now, before we go any further, let's have a look at the way to write metres per second. We can write metres per second like this, that we are used to, or does anyone know another way that can be represented? Right, with a little -1, so metres per second. That -1 means that it's underneath a fraction line. So that would be metres over seconds. That's metres per second, because the per line is basically the vinculum of the fraction. So that's how it could be written. Now, it's up to you. There's no more correct than the others. This is just easier for me to type on a computer. That one there requires me to put a superscript in. So you'll see me mostly using this one, but every now and then, especially for an exam, I might swap over to that one. Okay. So meters per second means velocity. Right, so what's my change in velocity? So I was here at 0, I'm stopped. So if I'm stopped at 0, and I suddenly, 3 seconds later, I'm travelling at 3, what is the change in velocity? How much does it change? Now, we use a symbol for V, remember that last time? V, the delta, E means changing, and V is the change in velocity. And change in velocity, if we do using common sense, change must be what you've got now minus what you had before. So if you go to the canteen at lunchtime and you come out of the canteen having $10, but you go in to the canteen having $50, big lunch, how much have you spent? You've spent, your change equals $40, isn't it? But in reality, it's your change is not, you haven't gained $40, that's, is it? You've lost $40. So what would be a nice way of representing that mathematically? That's a loss of $40. A negative, good. So that means, how do I get a minus out of all this? It's final minus initial. So a delta V would be final velocity minus initial velocity. Okay. So that's going to be the change in velocity. So let's have a look at what our final velocity is. What is the final velocity in this little section just here? What's it thrown to? Right, my final velocity is 3. What was my initial velocity? 0. So delta V, final, 3 minus 0 is 3. So that, is it a positive 3 or a negative 3? It's a positive 3, isn't it? 3, final minus initial, positive 3. That means we've gained 3 meters per second. Okay. Are we okay with that part first? Now we need to introduce acceleration. Acceleration is going to be defined as change in velocity. Remember that change in now has a specific mathematical meaning. It means final velocity minus initial velocity divided by the time taken that it takes to happen. That is acceleration. Acceleration will either be a positive number or a negative number or 0. We don't use the expression deceleration. It doesn't actually exist. That's a layperson's term that has no idea of physics. So, the final velocity is 3 minus the initial velocity is 0. That's what we just discovered. Divided by how long did it take for this to happen? It took 3 seconds. So that gives us 1 meter per second every second. Now, just before you copy down that 1 meter per second, let's see what that means. What that says here, that for every 1 second I go sideways, I'm changing 1 more meter per second faster going up. So after 1 second, I'm travelling 1 meter per second. After 2 seconds, I get another 1 meter, which means I'm now 2. At 3 seconds, I'm travelling now at 3 meters per second. So for every second, I gain 1 meter per second. So I get 1 meter per second every second. Are we okay with that? So the unit of acceleration is the meter per second per second. Now that sounds hard to say, meter per second per second. And a few moments ago we said, well, that actually is a fraction. Meter per second is meter per second, isn't it? And then it's per second. If we were to use that as a fraction, So just say we had A on B all on C, that actually equals A on B, C. You do the mathematics there. So that second comes down there, and that means that the actual will be metres per second squared. Okay, so the metres per second becomes metre per second squared, and because it's on the bottom of a fraction, that's also metres per second is little minus 2 there. Okay? So we're not going to call it metres per second anymore. We are now going to just refer to it as metres per second squared. Are we okay with the unitage now? Why is it that rather than metres per second? Okay, now that means that we have a formula. We use our formula for acceleration, which is just simply logic. Then we realise that the gradient of this line must also equal the acceleration. So let's have a look at the gradient. Remember, the gradient is equal to vertical rise over horizontal run. The vertical rise here is 3. That's the change in velocity. Horizontal run here is also 3. That's a change in time, and it equals 1 metres per second, and it's moving forward, so it's a positive one. So we now have 2 ways of finding the acceleration. We could use the formula, which is here, or we could realise it also equals the gradient of the graph. Are we okay with both of those forms? Okay. Any questions so far? Okay, so let's work out the following questions. Over here on the side, we have to work out the velocity at 1 second. How would I work out the velocity 1 second with a velocity time graph? Right, we simply read it off. Okay, at 1 second, I'm travelling at 5 metres per second. How fast am I going at 3.5 seconds? So 3.5 seconds is here, and so I'll be travelling at 3 metres per second. So we can simply read those ones off. The next part is we're asked to find the acceleration during the following intervals. A to B is this one here, which we just found out that A here would equal 1 metre per second squared. So that's easy to do A to B, that one there, A to B. Now let's do B to C. Get rid of that. What would the acceleration during this little section here be? It's 0. Why did you immediately go for 0? Good, exactly. There is no change in velocity. The acceleration here equals 0 metres per second squared. And remember, there are 2 ways that we're working out acceleration. Acceleration is equal to change in velocity over time, or acceleration equals the gradient on a travel graph where it's velocity against time. That is horizontal, so the gradient is 0, or is there any change in velocity? There is no change in velocity. Velocity remains for this entire interval between 3 and 4 seconds at 3 metres per second. Okay, what about C to D? Well, let's use I'll rub that part out so we can see it. C to D here. Okay, let's use the gradient. The gradient's the easiest way to do this. What's the vertical rise? 3. What's the horizontal run? So what must the acceleration be in this section equal? It's 3 on 1, and it's 3 metres per second squared. Okay. As we pass, this is horizontal, so what must the acceleration up there be? 0. Now, let's have a look at this section just here, going back. Okay, now, this is what gets most people totally and utterly confused. Firstly, is that a negative or a positive gradient? Negative gradient. So this means it's the acceleration will be negative. Is the particle, the whatever it is, that's the car, the bike, the person, is the person moving forward or backward during this purple little section here? Still going forward. So they're still moving this direction, but they are getting slower. Does that make sense? Okay, so let's work out what the acceleration is in this part. Well, let's do it by gradient. Gradient is the easiest way. So vertical rise is 2 over horizontal run, which is also 2. And because it is negatively sloped, it's minus 2 on 2, which is negative 1 metre per second squared. Okay, are we okay with that? Let's do it now, rather than do it by the gradient. Let's also do it by the formula, because we need to be able to do it by the formula as well. To do it by the formula, I'll put it down here. Acceleration is change of velocity over time. That's our formula. Change is defined as final minus initial conditions. What's the final velocity? It's found here. What's that level? That's 4. So it's 4. What's the initial? During this part, what was the first velocity that was travelling at? It was travelling at 6 over here. So there you can see why it becomes negative 2 on the top. What's the change in time? 2 seconds. So it becomes negative 2 on 2, which is minus 1 metres per second squared. Are you okay why it has to be final minus initial, otherwise you will not get the right values? Okay. So that's the first thing you can use the velocity versus time graph against. This little section just here. It has to be a velocity of time graph, then you can find the gradients represent acceleration. The second thing that you can use a velocity versus time graph to do is to determine your displacement. The area under a displacement graph, area under a velocity versus time equals displacement. There's the definition. So you can actually work out how far it is moved during this time. Now remember, it's either moving forward or it's moving back. So displacement has to be used, when you're doing this, you have to use the common sense. So let's work out how far it has moved during this time period from 0 to 3, which is interval A to B. So just finding or shading in that area, it's this area here. Now when you're in year 12, you'll understand that areas under graphs have significance, part of calculus. That's the integral it's called. So at the integral, the area under velocity versus time graph is displacement. So all I have to do is just work out this area here. All I need to do is use a triangle formula. So let's work it out. The area of a triangle is a half base times height. What's the base of the triangle? 3. And what's the height of the triangle? 3, so it equals 4.5. Now displacement is measured in meters per second squared, kilometres, hours, seconds. What is it? What's the displacement going to be measured in here? It's meters, isn't it? How do I know it's meters, not kilometres? Well, everything's in meters per second. Displacement is meters, isn't it? And it is moving forward, so it's moved. The displacement is 4.5 meters 4.5 meters forward. To the right, positive, whatever you want to say, forward. Forward from where? From where, not from the origin, from your starting point. Does everything have to start at the origin? No. Remember, displacement is defined as how far you have moved from your starting point. Okay. Are we happy with how that works? Okay. Just pausing that there. Okay. Now, we're going to now follow the instructions on the side over here, which says we need to calculate the velocity at time 10, at the start, and then calculate accelerations and so on. So let's do one after each other. So let's firstly, how fast are we travelling at time equaling 10 seconds? So here is time equaling 10 seconds. How do I work out how fast we are travelling? I just read up and sideways. I'm travelling at 40 metres per second in the forward or the backward direction. Forward. So it's 40 metres per second forward. Other words that we could use for forward would be to the right. If this was a vertical and horizontal motion, so vertical motion could be up, okay, it could be up, outward, inward, and all those other words as well. You have to just read the question as to work out what it's referring to. Okay, it could be also travelling north. Okay, that? Yep.
So when it's a straight flat, like that way line,
it's still moving, yes. It's travelling at 6 seconds, it's travelling at 40, and at 16, it's also travelling at 40. It's not accelerating though. Okay?
So when
It's
so
only
when it's like that, when it's moving?
that's a displacement versus time graph. So if we were having displacement on this place here versus time, when it goes horizontal, it means it's stopped. Once we have velocity here, that means it's still moving. Yeah. It's just not accelerating. Yeah. That's our hard part. This is what makes this difficult. Right, next. The next part says, what is the acceleration at the little star there? Just like we were trying to work out what was the velocity for an entire interval, what can you tell me about the acceleration from A to B? Is the acceleration changing or is it the acceleration constant? It's constant acceleration. Okay? It's a straight line. If straight lines means things are changing at a constant rate. So let's work out the acceleration during A to B. Now remember, we've got two ways of doing it, and I have to stress the two ways. The first is we can use the formula delta V on t, or the acceleration is simply the gradient of this graph. So let's just firstly work out with the gradient. What is the vertical rise of this here? It's 40 high. And what is the horizontal run? 6. So the gradient is 40 on 6, which is at 6 and something, 6 and 2/3 metres per second squared. Don't forget that that's the acceleration. How do I know it was metres per second squared? You just look at the units. Here is metres, here is seconds, here is seconds. Okay? So it must be metres and seconds that we're working with. Let's now use the formula. Now the formula says that we have to calculate the final minus initial velocities. So acceleration would equal final velocity minus initial velocity all over time. Right, yeah. Wouldn't it be nice if we had a symbol for final and initial velocity? It would have been lovely. So we do. We're going to now use, for final velocity, you're just going to use V, velocity, the final velocity. Okay? Initial velocity, we're going to use the other letter that maths loves, it talks about calculus, U. Okay? So this acceleration is going to now be called V, final, minus initial over T. So just to write what these means, that's final velocity and u, initial velocity, and t is the time taken for the change to happen. Right here. So I can still use that. That's the one that you'll be given on your formula sheet. This one here you will also slightly be given on your formula sheet. It will slightly change, and I'll show you the change later on. Okay. So using that formula here, can I write this up? Equals, the final velocity is 40, the initial velocity is 0, but it starts at stopness, and the time taken is 6 seconds. So if you pop that in the calculator, it's 6 2/3 meters per second squared. Okay. If you don't want fractions, you could just set equals 6.7 meters per second minus 2, and that's 1 dp, or 2 significant figures. Are we okay with that working? Okay. Right. The next thing we have to do is over here is calculate the acceleration during the interval c to d, which is this interval here. I first ask the question, which direction is this car, bicycle, runner, electron going? It's still going forward. But what's happening to it? It's slowing down, it's decreasing. Eventually, it's going to be so slow that it comes to this point down here at 22 seconds. What is it doing at 22 seconds? It's stopped, good. Because if you go here, what's the velocity? 0. Okay? Don't forget this is a velocity versus time graph. You've got to keep that in mind. It's telling about velocity. It doesn't say where it is, it just tells you what it's doing. Okay, so let's use the acceleration equaling v minus u on t. I could use the gradient if I wanted to, but this is exactly the same as the gradient, isn't it? V minus u, now the final velocity is 0. The initial velocity was 40. How long did it take for this change of the green? It took that part there, which is from 14 to 22 seconds, and that's 8 seconds. And that's negative 40 on 8, which is minus 5 meters per second squared. Okay. Are we okay with this? Right here. Just answer this question. What's the only thing that can cause a particle to move faster or slower? Force. It's a force. So all that the acceleration is telling us is a force must be acting. Okay? And it doesn't just tell us that a force is acting, it also tells us which direction the force is acting. This part here, this part just there, the particle is getting faster, isn't it? So the force must be acting from behind, pushing it forward. This part over here, it's getting slower. So the force must be pushing against it, slowing it down. Okay? So negative acceleration means the force is in the negative direction. Positive acceleration just means the force is in the positive direction. It's that simple. Okay? Right, the last thing we need to do is, we'll just go skip down to number 5 here, calculate the full displacement over the whole time. How do I calculate the full displacement that it has moved? Right, it's the full area underneath that section. So we want the whole part. Okay, we want to find it. What shape is this? Trapezium. Now, sometimes it's not going to be a nice trapezium, sometimes it's going to be an easy trapezium. You can always just do it by triangle, rectangle, or you can just apply the trapezium formula. If you like to count boxes, you can also count boxes. Okay, so area of a trapezium is half h top plus bottom. We all know that? Okay. I know there was some panic looks over here thinking, what is the business formula? So half times the height, here's the height of the trapezium. What's the height there? It's 40, good, yeah? The top There's the top. That's from 6 to 14, so that must be 8. And the bottom is 0 all the way to 22, so it's 22. 8 plus 3 and 2 is 30. Half of 40 is 20, so it's 20 times 30. It's 600. 600 what? Meters, good. Why not kilometres? Right, it's meters up here. So you get the units from the question itself. So this is 600 meters, and it's a displacement, so it's forward from its starting point. So the area equals that, and it's forward. Okay. Is the particle at rest at any time during this journey, excepting for when it starts and when it ends? It's only at time equals 0, there is it stopped, and there is it stopped. It's not stopped here, is it? What's happening to the particle at that point? It's still moving forward at 40. Excellent, well done. Okay. Rightio. Anyone got that? If you think it's stopped during this little section here, you are mixing it up with the displacement versus time graph. Okay, could you take a few moments to paste in the last of those graphs? Right, this is the last of the graphs. The reason why it's last, it's a much more complicated journey, isn't it? Remember, once again, before you do anything with a travel graph, there are two different forms. You look at the vertical axis. If it's velocity versus time, then it's a totally different thing than displacement versus time. Gradients mean different things. Okay? This is velocity versus time. It is not the same as last lesson, so keep that in mind all the time. Right, now let's have a look at the journey. Here is the 0 line, and a lot of people miss that. There is the actual time axis. Okay? Here is the vertical axis. So just putting that on there so you can see it. Above this horizontal line means the particle is moving in which direction? Forward. So it's moving forward to there. What's it doing from here there? It's moving backward. Okay? So do we know where it starts? Does it start at 20? No. We don't know where it is starting. All we know is at time equaling 0, it's travelling at how fast? It's travelling at 20. We don't know where it is, we just know how fast it's going. Okay? And it's moving in which direction? Forward. So it starts at time equaling 0, it's travelling 20 metres to the right, or to wherever that direction is, and it is travelling a constant velocity. Then what happens to it once it gets to time equaling 4 seconds? It starts to slow down. And when it gets to 6 seconds, here, what does it do for 2 seconds? It stops. So its journey is, it starts somewhere, mysteriously, we don't know where. It moves forward at 20 metres per second. Then for 2 seconds, it starts to slow down and it stops. Now it waits for 2 seconds, and then which direction is it going to travel now? Backward. It's going to then start getting faster. It's going to get faster. Okay? Even though it's travelling backward, it's at time equaling 10 seconds, it's travelling at minus 20 metres per second. It's got faster, hasn't it? It used to be 0, it used to be stopped. Now at E, it's travelling at 20 metres per second. But which direction is it doing it? That way. Okay? So 20 metres per second is as fast as 20 metres per second forward. So 20 metres back, 20 metres per second backward is the same as fast as 20 metres forward. Are you okay with that? Please don't apply integer rules to this. You can't say that 20 metres per second forward is faster than 20 metres per second backward. That doesn't make sense. Okay? That's the reason why we can't use the word deceleration. It's not decelerating. It's getting faster going backward. Does it stop during this little period here? No, it just travels for 2 seconds at 20 meters per second backward. Then, so it doesn't stop for that second there. Then it actually gets even faster going backward. It travels down, it gets faster towards 30 meters per second going to the left. Does it stop during this little period here? No, it just has 2 seconds where it's travelling at 30 meters per second in the negative direction. Then what happens magically to it? It starts to slow down until eventually at 22 seconds, what does it do? It's stopped. Has it stopped at the origin? No. Remember, this graph tells you how fast it's going, but not where it is. It tells you what it's doing, not where it is. The what, but not where. Okay, now let's do the actual calculations. Take a few seconds and I want you to calculate the accelerations in interval A to B, from there to there. You don't have to calculate there. D to E, there. And then H to I, there. Okay, off you go. Could you calculate those 3 there, please? Okay, let's see how you went. I do it simply by gradients. Gradients is the quickest way of doing it if you've not got a travel graph. So here it's flat, no acceleration. Here it's going back, sorry, it's negative acceleration, it's -10, we agree? Here it's 30 rise, vertical rise is 30, and it's the horizontal run is 4. That means that the particle is being pushed to the right. So if the particle is actually running towards the left, it's being pushed to slow it down. Okay, are we okay with all those? The last thing I want to work out is how far does it go? If I give you 1 millisecond, please. To work out how far it's travelled, displacement, that's travel forward, isn't it? This part here would be travel backward. If you travel forward, then travel backward, how would you know where you are? It's that minus that, wouldn't it? You have to subtract the 2 values. Okay. That's a beautiful part about this is you